Good morning, student. Today we are going to learn about MOSFET VI characteristic. Before drawing the characteristic, first we have to find the drain current equation. For that we use gradual channel approximation method. Using this method, we find out the drain current ID in linear and saturation region. And another method named channel length modulation is used to find out the drain current when the channel length starts to decrease from the drain side. So today we discuss about the gradual channel approximation method. For this method, first we consider the cross-sectional view of the N-channel MOSFET operating in linear mode. For that, first we connect the source terminal and body terminal to the ground. Because of that, the Vs equal to Vb means source voltage and the body voltage is equal to 0. And we set the gate to source voltage larger than the threshold voltage for creation of the channel or inversion layer in the MOSFET. And we have to remember that the VGS and the VDS value are the external parameters controlling the drain current. Next, we assume the coordinate system in this structure such that the x direction is perpendicular to the surface, means this one is the surface and this is perpendicular to the surface, and the y direction is parallel to the surface. So next we assume that electric field component in y direction is dominant compared to x direction, because as we know the flow of electron occur in only y direction. There is no movement in x direction. Only because of that the y direction is dominant compared to x direction. Next, the channel voltage is denoted by Vc of y. Here we consider two boundary condition, that is y equal to 0 and y equal to L. So the channel voltage when the y equal to 0 means the y equal to 0 is the origin point which is at source terminal. We know that from the beginning we connect the source terminal to the ground. Because of that the source voltage is equal to 0. So when channel voltage is at 0 point or y equal to 0 means origin point, at that time the voltage is equal to 0. But when y equal to L means this point, so this is the last point of the channel because the channel length is L. So this point is connected at the drain terminal, and we know we apply VDS value to the drain. Because of that the channel voltage at y equal to L we consider it at VDS. Let Q of y is the mobile electron charge in channel, and this one is the equation, that is Q of y equal to minus C of VGS minus VC of y minus VT0. So this equation is coming from a very basic equation, that is Q equal to CV. So V equal to the capacitance of dielectric between gate and substrate. So here the dielectric is the oxide between the gate and substrate, so that is the Cox, capacitance of oxide. Then these are the net voltage or actual voltage which is responsible for the electron charge in the channel, and the minus charge is given because of the charge of electron. As we know the charge of electron is negative, so minus is given. Next, Let's see the diagram. This is the simplified geometry of channel. Here the channel length is L, and from the diagram we can see the thickness of channel at source end is larger than the thickness at drain end. So we consider a fractional part of the channel, that is dy. Means this is the fractional part we have taken, and it has width and thickness to find out the area, and the length of this channel, this fractional part, is dy. And another thing, the net voltage throughout the channel varies, we know that. So when y equal to 0, this one is the net voltage. Okay, so when y equal to 0, the channel voltage is 0. So when y equal to 0, the channel voltage is 0, so that term is not given here, only VGS minus VT0 is written. Then when y equal to 0, at that time the voltage is VDS, so we put that value VDS, and the equation is V equal to VGS minus VDS minus VT0. So from these two equation we can see the voltage varies, means decreases towards drain. Now we will calculate the incremental resistance, that is dr. So the equation is dr equal to minus dy by w mu n q of y. So minus is given for charge of the electron, that is negative. Then the above equation derived from a basic resistance formula, that is R equal to rho L by A. Rho is the resistivity, which is represented as 1 by conductivity, 1 by sigma. So here we write 1 by sigma. Then L is the length of that fractional part, that is dy. Then area is the width into thickness, and here we consider the thickness as unity. Because of that, here we write dy by sigma into w. Then the sigma value is charge, then number of electron, then mobility of electron, plus number of holes, then mobility of holes. So this is the formula of conductivity or sigma. But in this MOSFET, the current flow is only depend on electron. Because of that, we neglect the whole part, we only consider this part. Because of that, we write dy by w qn mu n. So in the next equation we write dy by w mu n q of y. Here q into n, the charge into number of electron, is considered as considered as charge density. Because of that, we write here q of n. Next we calculate the drain current by using Ohm's law. As we know, Ohm's law is V equal to IR. Here we consider the channel voltage, that is Vc, and the channel voltage is varying, not constant. Because of that, dVc. Then current is drain current, so id, and resistance is the incremental resistance, so dr. We have the value of dr, so we substitute this value and get this equation. Then we just take the value, that is w mu n q of y, to the other side. So the equation is like this. Then we integrate the both side, and for integration As here dy is given, so boundary condition for y equal to 0 and L, so limit of the integration is also 0 to L. Then as we know, when y equal to 0, the channel voltage is 0, so 0 is given. When y equal to L, the channel voltage is VDS, so VDS is given as limit in the other side of the equation. And W and mu n are the constants, so we taken out, and here we integrate ID, as ID is the constant, we taken out that term, and L minus 0. Then we substitute the value of Q of y, then we write here the whole equation. After that we taken out the C ox, as this one is the constant, and minus cancelled out, this minus cancelled out, and in this equation the VGS and VT0 also constant, the only variable is VC of y. So after integration we get the equation in linear region. Then we take some constant, that is mu n C ox equal to K dash. So we put that value, we get this equation. Then K dash W by L equal to L. Then we put the value in the linear drain current equation, then we get this value. But when the drain current is reached at pinch off condition, means at saturation voltage, at that time we know that the voltage difference between VGS minus VDS equal to threshold voltage. So from this equation we get the value for VDS, so VDS equal to VGS minus VT0. As we get the value of VDS, we substitute this value in the above equation, means the drain current equation in linear region. After substituting the value and simplify the equation, we get the resultant, means final equation for drain current in saturation region. So this one is the VI characteristic. First one is the transfer characteristic, this one. So transfer characteristic is the curve between drain current versus gate to source voltage. The current through the device will be 0 until the gate to source voltage exceeds the threshold voltage. So this point is the threshold voltage. Once VGS crosses threshold voltage, the current through the device increases. Here it increases. Next, this one is the output characteristic. It is the curve between drain current versus drain to source voltage. In this characteristic, with increase in VDS, means drain to source voltage, the drain current also increases until the pinch off condition, means this line represents the pinch off voltage. So up to that the drain current increases. After the pinch off condition occurs, the drain current almost constant even though we increase the drain to source voltage. But as gate to source voltage increases, means if we in first point is this, okay, VGS equal to 1, and up to this the ID current increases, after that it is remain constant. But when we increase the value up to VGS 2, so here the drain current again increases up to IDS 2. Like this, if we increase the value up to VGS 3, then drain current increases up to IDS 3. So if we increase the gate to source voltage, the saturation drain current also increases. So this is all about MOSFET VI characteristic. In the next class we discuss about the channel length modulation. Thank you.